Good morning. This is Hasan Turan from Capability Systems Center at UNSW Canberra. Today's talk is about the use of systems dynamic and its coupling with optimization algorithms to address the military asset management and resource planning problems. Even though this specific application is military, the methods and frameworks will be discussed in this presentation can be applied to another application domains. Okay, this is the outline of my talk. First, I will discuss what is asset management is. Then I will introduce how we will develop our system dynamic simulation model to address asset management as well as resource planning. Then I will discuss how we coupled optimization algorithms, specifically meta heuristics, to address different dimensions of asset management, such as fleet renewal, workforce planning, and finally some integrated problem such as facility location and capacity allocation problem. After introducing these simulation optimization problems and how we address them, we will introduce the risk behavior of the decision maker and how we handle this risk attitude against in this optimization problem. And finally, we highlight our future research agenda, such as integration of machine learning and artificial intelligence with systems dynamics models. Okay, let's start with the definitions. Asset management is an integrated activity to produce a value from a system of assets. Asset is a dictionary definition, a collection of systems to be considered for decision analysis. The key feature for an asset is that it should be significant enough to influence strategic decision and stakeholders' values. As you see from the figure, asset management and resource planning includes lots of different problems, from fleet renewal to the resource planning, to the workforce optimization, to the maintenance planning. I should say that these problems are not separate. So when you are trying to address one of them, you will probably encounter address another one. So I would say they are dependent to each other somehow. So we will discuss in this one in next slides. And we also need to define the term research. Resource to be a strategic resource, define it as a key determinant for the present and the future performance assets, not merely as a thing needed for the routine operations. Okay, why we use system dynamics in the asset management problems? First of all, asset management problems are path dependent. Decisions are long-term and largely reversible. The decision to buy a particular asset is a large investment with a long-term operational and economical impacts. For us, this study is started with the new modernization of the Royal Australian Navy, specifically submarine acquisition, and it was that time it is estimated that over 50 billion Australian dollar will be invested. So it shows how much the economical impact in this kind of problems. And second, in dynamic complexity. The asset management problems has a dynamic complexity. The performance and selected strategy influenced by the feedback interactions among the decision made by the dispersed function and division, as I showed in the previous figure. So if you want to enlarge your fleet in the next 10 years, so indirectly you have to increase your crew and maintenance technicians as well as the facilities. So they are dependent to each other. So as well as asset management problems has delays and trade-offs, planners are faced with the challenge to make decisions now whose outcomes can vary at the different temporal scales and the performance dimensions. So if we want to reduce the size of our crew, so we have to reduce our recruitment rate, but this does not immediately affect the total size of the crew. We will observe its effect like next 5 to 10 years maybe. So it shows the delays between the decision made and the observation of their effects. And finally, tightly coupled systems asset management problem has that functionality as well. So sharing resources among different entities and activities create tightly coupled relationships among assets and their constituent system. So for example, the assets such as submarines may be used for the national defense operational use as well as the training of the crew. So how much about of the time you will use it for the operational readiness and for the training of the crew. So there's another problem that has to be addressed in the asset management. So this type of properties nicely can be addressed with system dynamics. That was the main reason that we developed our simulation model with system dynamics. So, okay, to build our model, we use object-oriented and hierarchical structure. For each, we divided our problem to the different submodules, such as acquisition, retirement, maintenance, operations, and crew modules, and they interact with each other. So when we coded our model in AnyLogic, which is developed in Java, so we make some fine tunings as well while we are developing, not straightforward AnyLogic implementation. So these are the brown boxes shows that the strategy means like a decision variable that you can interact from the decision maker and how it is affected the structure as shown in this figure. And this is the causal loop diagram, some kind of causal loop diagram we use while we are developing our simulation model. So I will not discuss too much about this one. So this is the final product. So middle step 2 is the model itself, simulation model. And first one is the strategies, inputs, you may say, articulated by the decision maker. Then at the end, the last step is generating KPIs, indicators. Then based on these indicators, decision makers change its strategy, vice versa. This is the decision-making loop. So we use Excel sheets that decision maker populates. Then we also create Excel spreadsheets to nicely plot, create visualization. So you can see the details of this paper in the Journal of Simulation. So far, we use only simulation model. As you know, simulation model doesn't provide the optimal solutions. Simulation model doesn't equip with the finding optimal strategy. That's why we couple our simulation model with optimization algorithms. So optimization algorithms themselves look for many strategy in a short amount of time compared to the human behavior. So by meaning strategy, we mean set of input variables. Sometimes we call it factor or parameters. So it is the main concern of interest that we want to optimize. As I mentioned, there might be many feasible solutions, and to check all of these feasible solutions with the simulation model, run it, observe the KPIs, go to the second one, go to the third one, might be computationally prohibitive. That's why we need the optimization algorithm. That's why we need to couple them with the optimization algorithm, which is called as a simulation optimization or simulation-based optimization. And the figure nicely shows the main idea of simulation optimization algorithms. As you see, simulation model is fit with the input parameters that are generated by the optimization models, and responses, KPIs, fit into the optimization model, and optimization model looks for better decision. So this is the main framework for the simulation optimization. Okay, to test the first simulation optimization in asset management, we choose the fleet renewal problem, and we hook the acquisition and the retirement module to the optimization algorithm, and we keep the other ones such as maintenance, workforce, operation model to the simulation model. So we observe many KPIs, operational availability, resource utilization, waiting time for the resources. But main objective was the maximizing the operational availability. So for the algorithm inputs, like for the genetic algorithm that we use, like the crossover, mutation probabilities, and we also add the uncertainties and the input parameters such as the failure of the maintenance equipment, etc. So this is the solution algorithm that we use. For the fleet renewal problem, the aim is to find the exact time of the replacement to retiring the old fleets and the acquisition of the new assets so that the operational availability stay maximized. Details of this present paper can be also found in our published paper in 2020 from expert systems with applications. So what kind of optimization algorithm we use? Not specific to the fleet renewal problem, but for all of simulation optimization problems in the asset management context. We use genetic algorithms, simulated annealing, NSGA2, NSGA3. So for the meta heuristics, that you have to encode the solution for the specific of the fleet renewal. We use two-layer array in the first dimension, acquisition date and retirement date, as well as in the sub-layer region of the retirement or region of the assignment of the assets that show when the asset phase go to the maintenance or go to the crewing. So it is an important thing for the submarine fleets. And the right figure shows the visual illustration of one of the state-of-art algorithm that we use, multi-thread simulated analytic algorithms, start from different solutions, converge to optimized solutions, compare it to the another algorithms. It provides much better solutions. Let me show that one. So these are the brief results of this fleet renewal problem. From the box plots, blue ones are the multi-thread simulation algorithms that we developed. As you see, provides more fleet operational availability, as well as it is tight boxes, so which means that they are more robust. On the top chart, red dot shows the capability threshold that we want for submarine on average every unit of time point. Our algorithms usually provide that one over the 4 submarines. And this is the shaded area, shows the 95% confidence interval. So, and the dark gray shows the average. So on average, we are mostly above the 4 submarines, and in some situations there might be possibility going to capability threshold. So that was the main output of this research. So we want to go another step ahead. So rather than just investigating fleet renewal, we want to investigate its relation with the workforce planning. With the workforce planning, I want to specifically highlight it is crew planning, not a maintenance technician. So the reason was that, so the personal spendings for the military in Australia, like 2019, it was like 32% of the total spendings for the personnel. So for our problem, fleet renewal problem, same as the previous problem, retirement dates, commissioning dates, and the decision variable for the workforce side is how much I should recruit in each time period, how many I should promote, and how often should I promote to the next ranks. So there was a career structure, career progression of the crew, as well as discussed in this problem, such as I showed on the left side figure. Top side is the fleet renewal, and the workforce side is the supply side. So it is like a supply and demand matching problem. So at the end, we generated how for each rank surplus and shortages for each type of workforce. Each type of workforce, we used only officers and sailors to differentiate the workforce types. And the most important results for us was the most important rank is not the first rank or the last rank. Middle ranks are causing the trouble. So there was a shortages, especially for the rank 2. And for the details of this paper, it is published in 2021 in the European Journal of Operational Research. So far I discussed the single objective, operational availability maximization, cost minimization. But while we are solving the joint problems, we encountered them converting everything such as fleet availability to the monetary values is not that easy, and it's open to debate. So rather than using single objective optimization problems, we change our direction to the multi-objective. So we use multi-objective methods to model our problem as well as to solve our problems. In this one, we specifically cost minimization, fleet availability maximization, and inter-region transaction minimization, which means that if one submarine assigned to the one region, you should go to that region for the maintenance and crewing unless it is necessary to going other regions. So in each that time, we counted how many times this happened. So it is like a penalized thing. And we use decision variable location of the maintenance facilities, their sizes, and the time of the expansion and the time of the downsizing decision, which submarines is located to the which facility, as well as the capacity, workforce, the technician capacity, and crew recruitment decision. So it was a quite large problem. We use NSGA2. So I will not discuss the detail of it, but compared to the previous algorithms, rather than finding one single solution, these multi-objective algorithms come up with the multiple solutions as shown here. So we presented the results to the decision maker to pick the best one based on their preferences. So the result of this also published in 2021 in the Expert Systems Journal. So I would like to discuss another topic, how we integrated our simulation model with the decision makers' preference towards the risk. So far, we were using the expected maximization or expected minimization, but sometimes it might be required to be ready for the worst case scenario. So we integrated, which is known as conditional value at risk CVAR value. So we use not only the expected value, but also the worst 5 percentile. So this is the algorithms frameworks, methodologies framework. While we are considering the separation as a random variable, as well as the maintenance cost as a random variable, at the end, we also obtained Pareto solutions, and we use multi-criteria decision-making called TOPSIS to pick the one, depending on the user preferences. So some results, as you see, we have now two colored Pareto solutions, one for risk averse and one for risk neutral case. And these are the schedules, charts for the fleet renewal schedules. As you see, in some cases, there is an empty space between the retirement of the old assets to acquisition of new assets. So it says that sometimes it might be possible not to hold any fleet. So it was an extreme situation that I want to highlight. So there is one also published recently in Computer Science and Industrial Engineering Journal. So what is the next step? So you may ask, is system dynamics the best way to model this problem? Probably not. I will say the hybrid methods, some part might be modeled as a system dynamics, other parts of the problem might be modeled as for example, discrete event or agent-based. For the maintenance problem, I will go with the maintenance discrete event. For the crew planning, career progression, agent-based might be better options. Some of them is I was using just a probability distribution based on the past data for the separation of the workforce. It might be adding more granularity, like who to promote, who to recruit, who will leave the crew next. So we may use machine learning. That's what I am working on right now. Or optimization algorithms are quite static, which means is that you decide the optimal decision without considering the future's outcome. So maybe using like a deep reinforcement learning, doing the dynamic decisions throughout the time period might be enhanced our methodology. So thanks for your attention. If you have questions, I will be happy to answer during the live presentation. Thank you.